Hello and welcome to our channel, The Global Tutor. We have another explanation video today. We'll be looking at and thoroughly explaining Newton's third law. Now, if you've watched any of our other videos or taken one of our courses, you'll know that we provide in-depth explanations of key physics concepts. If you didn't understand it before you watch one of our videos, you'll understand it when you're done watching. You're probably watching this because you're studying physics in high school or university. We'd like to help you, and we'll happily produce a free video explaining a physics concept that you are having a hard time understanding. If you'd like for us to do that, then just let us know in the comment section. We'll do our best to help you. And if you really want to master Newton's laws and dynamics, check out our Udemy course. It's great for AP Physics, A-level, and other pre-university or early university courses. Let's get right into Newton's third law. Newton's third law can be stated as follows. For every action force, there is an equal but oppositely directed reaction force. Another way to put this is, for every action force which we can identify an equal force which is a reaction to that force. Now let's get this correct from the onset. Newton's action and reaction forces form pairs, but they never ever act on the same body. I like to explain it as follows. If we have two bodies, body A and body B, and body A exerts a force on body B, body B will exert an equal but oppositely directed force on body A. Notice, the first force is the force that body A exerts on body B, and the second force is the force that body B exerts on body A. The first force acts on B and the second force acts on A. Together, these forces form a Newtonian action-reaction pair. And those pairs never ever act on the same body. Okay, so let's have a look at a couple of examples. The first example is an object which rests on a surface. Now this object, because it has mass, will have a weight. And that weight will be transmitted through to the surface as a contact force. So the object exerts a contact force on the surface. This contact force is equal to the weight, but it's not actually the weight. It's just a push. So it's the same as if you are sitting on your chair right now, you lift your feet off the floor, then you are exerting a push downwards on the chair. And you can feel that on the seat. Okay, you're exerting a force downwards on the chair exerts a force upwards on you. So the object exerts a force downwards on the surface exerts a force upwards on the object. And these two will always be equal. If they weren't equal, then either the object would accelerate downwards, or if the force which the surface exerts on the object was greater, then the object would bounce upwards, and that doesn't happen. So we can draw the typical situation when somebody is sitting on a chair. So that is a chair, the legs of the chair resting on the surface. Somebody sitting on a chair, and we'll draw them in simple typical physics stick men. Okay, that person exerts a force downwards on the chair. In order for that person to be in equilibrium, for the person not to either accelerate downwards or accelerate upwards, i.e. for that person not to fall, then the chair must exert an equal but oppositely directed force on the person. And we have the Newtonian action-reaction pair, which is the force that the person exerts on the chair and the force that the chair exerts on the person. We could then extend that to think about the force that the chair exerts on the ground. The other side of that force, which forms the action-reaction pair, is the force that the ground exerts on the chair. So for each one of those cases, one could draw a free body diagram, which would help to understand that particular case. So this is an example of a contact force that leads to an action-reaction pair. Let's look at an action at a distance force. Here we have the Earth, and we have a mass which is above the Earth's surface. We know that the Earth will exert a force on the mass, and that force appears as the weight of the mass that acts towards the center of the Earth. And believe it or not, this mass also exerts a force on the Earth. So the Earth pulls on the mass, and the mass, because it is a mass in the same way as the Earth is a mass, but it's a much smaller mass, it also exerts a force on the Earth. So why don't we have a situation, you may ask, where the Earth is being pulled in all sorts of directions by all of the masses which are above the surface of the Earth and exert a force on the Earth? Well, the simple answer to that is that the force that the Earth exerts on the mass is large enough to accelerate the mass. So if you lift something up above the surface of the Earth, the force that the Earth exerts is large enough to make it accelerate towards the Earth. So if you had an object with a mass of 1 kilograms, the force that the Earth would exert on that object is equal to 10 newtons, and that would be enough to make that object accelerate and fall towards the Earth. But that equal force of 10 newtons exerted on the Earth is not enough to move the Earth, because the Earth is massive. Remember our discussion about inertia. The Earth is very, very massive. It's got a large mass, so it's got a large inertia. So this is an example of an action-reaction pair for an action at a distance force. Similarly, if you had a positive charge and a negative charge, the positive charge would exert a force on the negative charge, and the negative charge would exert a force on the positive charge, and this would form an action-reaction pair. And again, this is an example of an action-reaction pair for action at a distance forces. The next example that we're going to look at is quite an interesting one, and a fortunate one because it allows us to walk around and allows cars to move on roads. The way that we walk is with one's foot or one's shoe in contact with a surface, one pushes back on that surface. And you can try this if you stand up for a moment and you start to walk forward. What you're doing is you are pushing back on the floor. The floor then pushes forward on you. So the force that you exert on the floor leads to an equal and oppositely directed force that the floor exerts on you. And that is the force which then accelerates you forward. So you'll know that if you want to accelerate at a higher rate, you exert a larger force on the floor. So the floor exerts a larger force on you. And so you have got a larger acceleration. If we look at the example of a motor vehicle whose tires are in contact with the ground, those tires rotate, in this case, in a clockwise fashion. That exerts a backwards force on the ground. The ground then exerts a forward force on the tire. And by exerting a forward force on the tire, what that does is exerts a forward force on the car itself. So these are Newtonian action-reaction pairs. Remember, they always act on different bodies. And they're easily identifiable. A good idea when looking for action-reaction pairs is always to draw a diagram.